So the secret code of creation. What if people discovered a code built into numbers? Numbers, 1, 2, 3, 4. What if they found a pattern, a code built into there, and it spelled out some kind of message? I mean, that would be phenomenal, wouldn't it? Because numbers are not something that we humans created. They're something we discovered, and the properties between numbers. And so it would mean that the creator of numbers, the mind responsible for numbers, it tells us something about that mind. That would be something that's fascinating, and it turns out that's actually true. That's actually the case. In the 1980s, mathematicians and using computers were finally getting fast enough in the 80s where they could discover these patterns built into numbers by the creator of numbers. And the results are remarkable, beautiful, amazing, and have no secular explanation whatsoever. So what we're going to see today is a little glimpse into the mind of God for which there is no evolutionary explanation. And before we get to that really good stuff, we got to start with some of the more difficult stuff. It's kind of like when I was a little kid and my mother would prepare these very good meals, but occasionally she would put broccoli on my plate, and that's just nasty. But in rare moments of maturity, I would occasionally eat the broccoli first, get it out of the way. Ugh. Then I can enjoy the rest of my meal, right? In that same spirit, we're going to do some broccoli first, but stay with me because it's going to get really good. It's going to get really interesting. I think this is mind-blowing. It was mind-blowing to me. I hope it will be that way to you as well. So the broccoli stuff, first, some definitions. A set is a collection of elements with a common defined property. In terms of sets of numbers, a set is just what you think it is. It's a group of numbers that have a certain defined property in common. And you can define different kinds of sets. That's not a problem. In most sets, some numbers are included while other numbers are excluded. Okay, so some numbers belong to the set, other numbers don't belong to the set. That's pretty easy. Consider the set of even numbers. Well, if we consider the set of even numbers, these are the ones that would belong, and the other ones would not belong. That's pretty easy. And that one's really easy to detect because you know that if a number, when it's expressed in a decimal format like that, if it ends in 0, 2, 4, 6, or 8, is even. If it doesn't, it's not. So there you go. That was pretty easy. Or we could consider the set of negative numbers. Now this is a different set, and so different numbers will belong to this one. But it's pretty easy to tell because all you have to do is look for a little negative sign in front of the number, and you can say it belongs to that set. So those ones are easy. There are sets that are defined in a way that's a little bit more complex, a little more complicated, such that you can't tell just by looking right at the number immediately whether it belongs. You have to do a little bit of work for it. I could give an example of the set of prime numbers, those numbers that are only divisible by themselves in 1 and no other integers. That one is a little bit hard. You can immediately tell it's not a number if it ends in 0, 2, 4, 6, 8, it's larger than 2. But you can't tell just by looking at it whether it belongs. And so the set we're going to focus in on is one of these ones that you have to do a little bit of work. It's called the Mandelbrot set. The Mandelbrot set is a set of all numbers, C, for which this sequence, Zn, which is another set of numbers, remains small according to that little formula that you see there. And that all looks very complicated, but it's not. So the point is C is the number that we're evaluating to check and see if it is a member of the Mandelbrot set. So C could be any number, 1, 7, 3, whatever. And then Z is another number that initially is 0, and then what we're going to do is square it, add it to C, and get a new number. That's what the n plus 1 means. So you have Zn, that's like the first value of Z. N plus 1 means the next value of Z, and the next value of Z, and so on. And the best way to do it is just to run through a couple of examples, and then you'll see very quickly, conceptually it's not difficult at all. So the question is the number 1 part of the Mandelbrot set? And so we're going to set C equal to the number 1, right? And then we plug it into our little formula, so Z squared plus 1, because that's the number we're checking, becomes Zn plus 1, which means the next value, the new value of Z. And so the initial value of Z, by definition, the first Zn is 0. Always starts with 0. Okay, that's part of the rule, part of the definition. And so you're going to have 0, plugging that in for Zn, right? 0 squared, 0 times itself is 0, right? Plus 1 would be what? 1. Good, thank you. The Common Core folks are still confused, but the rest of you got that. 0 plus 1 is 1. Okay, now that's the new value of z. I'll put that there, which means we put it back into the equation. Now we have 1 squared, which is 1 plus 1 is 2. Okay. You guys are math phobic, man. Woo. All right. Put 2 back in. 2 squared, 4 plus 1 is 5. Good. Put that back in. 5 squared is 25 plus 1 is 26, right? Put that back in. 26 squared is big number. Okay, you see what's happening here. We don't have to do any more than this, because remember the definition of the point that belongs to the Mandelbrot set is the sequence of z stays small. Is it? No, it's getting big. And you can see it's just going to get bigger and bigger and bigger. We can see the pattern. So is the number 1 part of the Mandelbrot set? No, because z did not remain small. You got it? So conceptually it's simple. You just plug the number in, and then you run z, starting with 0, you run through that formula. It'll either get big or it won't. If it gets big, it's not a part of the Mandelbrot set. If it stays small, it is a member of the Mandelbrot set. We'll do one more. I know it's a little tedious. Let's try negative 1. Is negative 1 part of the Mandelbrot set? So now we've got z squared minus 1 is the new value of z. Okay? Z always starts at 0. So initially we have 0 squared, which is 0 minus 1 is negative 1, right? Put that back in. Now negative 1 squared would be positive 1. Minus 1 would be 0, right? So we put that back in. 0 squared, this looks familiar. Minus 1 is negative 1. Put that back in. See what's happening there? This pattern goes 0, negative 1, 0, negative 1, 0, negative 1. It'll do that forever, of course. You can see that. Does the sequence of z stay small? Yeah, it's never going to get any greater than, in absolute magnitude, than 1. So is negative 1 part of the Mandelbrot set? Yes, it is. You got it. Simple. Okay? You can do that with any number, but we won't because it's tedious. But so computers can do that quickly, of course. And so when computers started getting to the point where they were faster than the human mind in terms of being able to perform arithmetical calculations, really in the 80s, we were able to test these points very quickly. Now there is one more complication, one more thing that we have to cover before we get to the really good stuff. The Mandelbrot set also includes what are called complex and imaginary numbers. And I hate that terminology, especially imaginary numbers, because they do exist, but it's just a name. It's just a name. An imaginary number is the square root of a negative. Okay, so when you take an imaginary number and you square it, you get a negative number. And the lowercase I is sort of the most basic imaginary number. When you square it, you get negative 1. And again, the terminology is misleading because imaginary numbers do exist, and to add insult to injury, numbers that are not imaginary are called real. They all exist. It's just we have less experience with imaginary numbers. But this bothers people because how can you have a number that when you square it, you get a negative, right? Because when you square a positive number, you get a positive number. When you square a negative number, you get a positive number. When you square 0, you get 0. So how do you have a number that's not positive, it's not negative, and it's not 0? That's a little tricky for us to think about. But imaginary numbers, like anything else, as you gain experience with them, you become more comfortable with them. And so it's the same way like when you were a little kid and you're first introduced to negative numbers, maybe those didn't sit well. You think, well, how can you have less than nothing? That doesn't make any sense. You get a little older, you get a bank account, suddenly you realize, yes, I can have less than nothing. It makes sense. And it's the same way with the imaginary numbers. They do exist. It's just that most adults don't get a lot of experience with them. But they are a part of the universe of concepts that the Lord has created. So one way to think about imaginary numbers is if you consider a number line, and you got positive numbers to the right of 0, and you got negative numbers to the left of 0, where would you put an imaginary number? Well, how about up there? Now you see, it's not positive, it's not to the right of 0. It's not negative, it's not to the left of 0. And yet it's not 0, because 0 is here, and it's up there. You can think of the imaginary numbers as being along a different axis, you see. And then you multiply that number I by any real number, and you get other imaginary numbers. So you have, so we actually have, instead of a number line, we have a number plane. with the real numbers along the x-axis, the imaginary numbers along the y-axis. Again, those are just names. And then you can have a number that's off-axis too. You can have a number that has a real part and an imaginary part, and those are called complex numbers. So 1 plus 1/2 I is an example of a complex number. Now the nice thing about using complex numbers, since they have a real part and they have an imaginary part, you can plot them on a plane. Every point on a plane corresponds to one complex number, okay? And the real component gives you the x-coordinate, and the imaginary component gives you the y-coordinate. But it's one number, and so that's neat because you can, normally we think of numbers as being along a line, but the nice thing is numbers, if you include complex ones, are on a plane, and you can run them through various formulae. And imaginary numbers behave the same way as the real numbers. It's just, you got to remember, whenever you have an imaginary number squared, it's a negative real number. Okay? So what we want to do then is take a look at the Mandelbrot set, which consists of not only real numbers, but also imaginary and complex numbers. And let's make a map of the Mandelbrot set. Okay? And the nice thing, again, about computers is they can check these points quickly. All we're going to do is pick a point out here somewhere and run it through that little formula, and z will either get really big really quick, or z will stay small. If z stays small, the number does belong to the Mandelbrot set, and we'll color it black. We've already checked -1. Remember, we checked -1, and it went -1, 0, -1, 0. So it stayed small, so it gets colored black. If we had checked 0, we would find it also belongs to the Mandelbrot set, so we color it black. Okay, so black points are points that belong, and we'll have the computer check a bunch of other values, and lo and behold, these are all points that belong to the Mandelbrot set. Okay, so the computer just checks different sections there. And then points that do not belong to the Mandelbrot set, when the computer runs them through and the sequence of z gets big, we'll give them a different color, like maybe red. Okay, so points that do not belong. Remember we checked the number 1, and it went, 1, 2, 5, 26, 6, 76. It got real big real fast, so that's not part of the Mandelbrot set. We color it red. And we'll have the computer check these other values too. And computers don't mind doing imaginary numbers and complex numbers. And so as we plot more and more of these, a shape starts to emerge. What we're looking at here is a primitive map of which points belong black or do not belong red to the Mandelbrot set. And as we plot more and more and more of these points, the shape that emerges is very interesting. You might think it would be something simple like a circle, but it's not. The shape that emerges is very interesting and unusual. Here's the shape that emerges. So again, black, all the points that belong to the Mandelbrot set, red, those that don't. And I even shaded it so that points that don't belong to the Mandelbrot set but get big slowly, I give them a bright color like yellow. And points that don't belong, but the z sequence gets big quickly, they're farther away from the Mandelbrot set, I give them a darker red. Okay, so it's shaded based on how close you are to the Mandelbrot set, which gives it kind of a neat look and allows you to see the shape a little easier. So black means it does belong. Color means it does not belong to the Mandelbrot set, but it could be very close, so it's like yellow. So now we don't have to go through that formula because the computer's done it for us. The computer's gone through and checked every point there, and it's checked to see if it belongs or not. And the shape that has emerged is remarkable. So now we can just look at this map and we can say, does half I belong to the Mandelbrot set? Yes, it does, because it's colored black. How about negative half I? Yes, it does. How about 1.5? It does not, because it's red. You get the idea. Now, what's really fascinating is not so much that we're looking at a map of the Mandelbrot set, but the fact that the map itself is remarkable. And I'm going to get rid of the graph so we can take a better look at this. But you just keep in mind that where this is. So 0 is right here. The last real number that's on the Mandelbrot set is at -2. It's extensive, and then that's it. There are no more numbers after that are on the Mandelbrot set. And only numbers on that line, really. So, fascinating shape. So you'll see several substructures in this shape, which, I don't know, looks to me like kind of like a bug or a horseshoe crab from above. But in any case, you'll see some shapes here. The first shape that stands out is this large heart structure. It's called a cardioid. Now, interestingly, that is exactly the shape that you will get if you take a circle and rotate it around another circle, keeping your pencil affixed to a given point on the first circle. That is exactly the shape you will get. See? That's a cardioid. And that's exactly the shape that we find in the Mandelbrot set there. Isn't that interesting? It's a perfect cardioid. And then growing off of that cardioid are circles, perfect circles. And you can see the largest one is the one here on the left. That's called the main disc. But you have other circles growing off of it. And you can see here, if you pick that big one, you pick that one, there's other ones in between. There's a smaller one, smaller one, smaller, 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 smaller. There's an infinite number of them, actually. They get smaller and smaller as they go toward this valley down here, toward this connection point. So we see a cardioid, we see perfect circles, and this one, if I back up here, this one is centered. This perfect circle right here is centered on exactly -1 and has a radius of exactly 1/4. So it's interesting the sort of mathematical properties that this shape has. And then the other structure you'll see are, I call them dendrites, these little branches that branch away from the circles. You can see the circle right here branches off, and then it branches into branches and so on. They look almost like bolts of lightning off this section. So quite remarkable. So cardioid, circles, and dendrites. And if we can zoom in on this, because we can have the computer check a smaller region at higher resolution. And when we do that, for example, let's zoom in on this upper region here, we find that the Mandelbrot set has some really interesting properties in terms of its map. For example, this circle right here branches off into 3, including the trunk. It's got a trunk right here, and then 2 branches for 1, 2, 3. Okay. Now the next one on the left has 5. Can you see that? I know it's getting kind of small. 1, 2, 3, 4, 5. The next one is 7, 9, 11, 13, 15, 17. It's all the odd numbers. Each one of these has two more dendrites on it than the previous one. That's interesting. It's as if the Mandelbrot set knows how to count by 2. It can add up 2 to each one. And it goes all the way down to infinity, odd infinity apparently. And on the other side, that has 1, 2, 3, 4, right? And then 5 and 6 and 7 and so on. So the right side has all the numbers. And the left side has just all the odd numbers. That's kind of interesting. So, wow. What does that mean? Well, the Mandelbrot set knows how to count, apparently. The other thing that's kind of wild, too, if you take, you got 5 and 3. 5 plus 3 is 8. And if you look at the circle in between these two, the next largest circle in between these two, it has 8 tendrils. So not only does the Mandelbrot set know how to count, it knows how to add. 3 and 5 is 8. And that's true for all of them. 5 and 7, 12. 7, 9, 16. And even the ones in between. If you take the 8 and the 3, the next biggest one right there will be 8 plus 3 will be 11. So each circle in between the next largest 2 has the sum of the dendrites from the other 2. It's remarkable. It's remarkable. Absolutely amazing. So same way on the right side. It's true for all of them. One of the most interesting features, though, that the Mandelbrot set is what I want to share with you next. Let's zoom in on this spike over here. So you got the cardioid, the main disc, and then you got these dendrites. There's only one perfectly straight dendrite, and it's this one right here. You can see it branches off that way. And then there's a little black spot there. So I want to zoom in on that and see what that looks like. So let's have the computer check on that. And it turns out it's another Mandelbrot set. Isn't that interesting? It's a baby version of the original. Again, you have the cardioid, you've got the main disc, you have the different circles growing off. And again, you got the dendrites, but now we have dendrites on top of dendrites, which is kind of interesting. We do have a little more structure on the outside. That wasn't there with the original. So we zoomed in on a spike, and the baby version has extra spikes growing off of it. Could that be significant? And you'll notice, too, that this little baby Mandelbrot, this mini Mandelbrot, has a little spike growing off of it as well. It's got a little black spot there. What could that be? Well, we zoom in and, oh yeah, it's another one. Well, that's interesting. And of course, it's got spikes and spikes branching off the spikes. And it's got a spike on its tail there. And well, it's got a little black spot there too. Now, what could that possibly be? And of course, and you can do that forever. It's a baby of a baby of a baby and so on. That apparently goes on to infinity. And that shouldn't surprise us if we understand that God is responsible for numbers. Numbers are a reflection of the way God thinks. And therefore, we can see infinities in these numbers. And so look how much smaller that one is compared to the original. Rather amazing. And if you're wondering, there are no larger versions. This is the atom of the Mandelbrot set. You can't go back before that. That's it. It's not growing off of anything else. So anything that is like that, that has its own shape built into itself on smaller and smaller scales, is called a fractal. So the Mandelbrot set is one example of a fractal. And it's not just the entire shape that repeats forever. You can zoom in on any section of the Mandelbrot set, and you'll find that as you zoom in, the shape, you're expecting it to eventually stop and get less complex, but it doesn't. The more you zoom in, the more complex it gets, the more interesting it gets. You can zoom in and zoom in and zoom in forever, and it'll just keep going. It's really very remarkable. Isn't it fascinating? And beautiful, too. The internal structure of this thing is quite lovely. So you just keep going and keep going. And it gives just a little window into the mind of God. And there are computer animations that zoom in by a factor of, many trillions and so on. One of the coolest places to explore I found in the Mandelbrot set is this valley in between the cardioid and the main disc. And let's just zoom in on that a little bit. But as we explore this shape, let's keep in mind what it is we're exploring. All we're doing is exploring a map of those points that belong to the Mandelbrot set. Those points that we run into that formula, Z stays small. And so let's zoom in on this valley. We call this the Valley of the Seahorses. Because if you look over on the right, you look upside down, but you see seahorse shapes that are quite beautiful. Now, the colors in these plots are arbitrary, right? Black, just by convention, is points that do belong to the Mandelbrot set. And then points that don't belong, we give another color depending on how fast Z escapes. So we'll change the colors every now and then just to keep things interesting. But remember, bright colors mean it's very close to the Mandelbrot set, and dark colors mean it's further away. So you can see these points are very close to being on the Mandelbrot set, and then the black points are on the Mandelbrot set. So again, you see how those circles continue. They get smaller and smaller and smaller. And the dendrites that grow off them, remember how they go from 3 to 5 to 7 to 9 and so on. Here there's so many, they spiral around and form that seahorse shape. So let's zoom in on one of these seahorses and see what they look like. And I have to explain here, because remember I told you if it's very bright, that means it's very close to being on the Mandelbrot set. You say, well, that doesn't look very close. It looks like it's way out there, right? What's happening here is there are very thin threads that branch off that are actually part of the Mandelbrot set. So there's a very thin black thread that goes out there and wiggles around. And it's incredibly wiggly. So it's just that it's so thin you can't actually see any of the black. But there are black points out there. The Mandelbrot set is a connected set. It doesn't have any islands. Everything that's on the set is connected to everything else that's on the set. An infinitesimal ant could walk from any place on the Mandelbrot set to any other without having to skip through the blue areas. So just think about how wiggly that thread is, that it will get out there and wiggle around and produce this incredible shape that you see here. We know it does that because the bright blue indicates it's very close to being on the Mandelbrot set. So it must do that. So what happens when we zoom in on this seahorse? You get kind of a web-looking structure, like a spider web type thing, where you have spokes going out and crossing over as well. Now, I found that if you zoom in on the middle of that, you can do it forever, and nothing changes. It's just remarkable. It goes into infinity in the opposite way, I guess. It goes to infinitely small without ever ending. And so let's go a little bit off center and zoom in on one of these threads and see what the threads are made of. And you find the threads are made of more spider webs, actually. They're made of smaller spider webs, see? And you get these little spirals as well, single spirals. And then there you have these structures in the middle where you have 1, 2, 1, 2, and then it looks like there's something in between them. Let's zoom in on one of those. And the interesting thing here is you go from the central hub of that spider web and the central hub of that spider web. There's 2 of them. In between, there's 4. 1, 2, 3, 4. And we'll find as we zoom in, it'll go to 8, 16, 32, 64, 128. Multiplies by 2. So not only does the Mandelbrot set know how to count, but not only does it know how to add, it knows how to multiply, at least all powers of 2. So let's zoom in on that central 4. And it goes to 8. And look what's in the middle. It's another baby Mandelbrot set. Now this time we zoomed in on a spider web that's kind of twisted around, and so this Mandelbrot set is a little bit turned relative to the original, but it's the same basic shape. Isn't that fascinating? You have the cardioid and circles. It's eerie. It's almost like God really likes this shape because you can find it everywhere. It's rather remarkable. And look how small this is compared to the original Mandelbrot set too as we zoom back out. Look how tiny that is. Again, just gives you an infinitesimal window into the mind of God. Let's go back to the Valley of the Seahorses. We went to the right last time. Let's go to the left this time. The left, you'll find what they call the Valley of Double Spirals. And I find this to be one of the prettiest places on the Mandelbrot set. These double spirals are spectacular. It's a double spiral, meaning you have two threads that wrap around each other. This thread right here is not the same as this thread, right? Because you can see, if I follow this one around, this one's in between it. This thread is the same as that thread. That thread's the same as that thread. Does that make sense? So it's a double spiral. And that's interesting to me because spiral galaxies tend to be double spirals. So I look at that and I'm like, a galaxy. Always neat. Now if we zoom in on that, every now and then PowerPoint says, I just can't handle it. So I gotta restart. There we go. If we zoom in on that, lovely substructure. Isn't that gorgeous? You're looking at a map of an equation. That's all this is. And the substructure is gorgeous. It's really pretty. All kinds of different structures. You can see more of these galaxy-type spirals. See this? You see the spiderweb-type structure like we found in the seahorses. And you find this structure here. I call them bow ties. For some reason, it reminds me of a bow tie, I guess, a little bit, because you get that twofold symmetry there. If we zoom in on one of those bow ties, you'll see you have the bow ties are made up of two double spirals, one there, one there. They cross over in the middle. And it goes to 4, 1, 2, 3, 4. If we zoom in on that. And then lo and behold, right in the middle is another baby Mandelbrot set. This time we zoomed in on a spiral, so it rotated around. And in fact, you can see this baby really happens to be flipped about 180 degrees, just because that's the one we zoomed in on, relative to the original. So the cardioid's on the left, and so on. And you can see it's surrounded by this beautiful substructure. Isn't that gorgeous? Now keep in mind, no human being created this. It's not like somebody sat down and said, I think I'll draw a heart shape and then a circle and so on, and then I'll put all this sort of graffiti out to the side. No, this is an equation that you're looking at. One that's infinitely complex, and the more you zoom in on it, the prettier it gets. Really pretty amazing. You can imagine the shock when people in the 1980s began running that equation through the computers and they started discovering these shapes built into math, built into numbers. What does that mean? Another place that's fun to zoom in on is the cardioid itself, this valley over here, which they call the Valley of the Elephants. As we zoom into that, you see why they call it that. Hopefully, this is the only symmetric valley on the Mandelbrot set where the top and bottom are identical. And you can see it looks like little elephants marching along, one after the other. And then on the ceiling, too. They're hanging on the ceiling. And so if we zoom in on a couple of these, you can see that each circle has one elephant on top of it. Maybe it's a circus elephant ball balancing on top of the ball there. That's kind of what they look like to me. They got the trunk that curls up. So, and we already mentioned there's an infinite number of these circles, right? As you go in, they get smaller and smaller. There's an infinite number of them, which means we have an infinite number of elephants here. Remarkably, each one has an extra dendrite from the previous, and their trunk gets increasingly curly as you go further and further in, interestingly. So what happens when we zoom in on one of these elephants, maybe the spiral trunk? Well, that spiral trunk goes on forever. It continues to zoom forever and never ends. So again, we go off to the side, and we find, again, some of the shapes that we've seen. You find sort of elephant-like structures in there. But you find these spiderweb-type shapes. You find some spirals, single spirals this time, not double spirals. You again find these sort of bow tie structures. But this time they're made of single spirals instead of double spirals. But the overall shape is similar. Isn't that gorgeous? And again, it goes from 2 to 4 to 8 to 16. Right? So there's the 4, 1, 2, 3, 4. And then 8, 1, 2, 3, 4, 5, 6, 7, 8, 16, 32, 64. And right in the middle again is a baby version of the Mandelbrot set. So it's absolutely amazing. And to think of what we're looking at a map of numbers. And who could have imagined that it would have such beauty built into it? Really remarkable. All of that, just a map of what numbers belong to z squared plus c. That's what we're seeing. And I just scratched the surface. This is an infinitely complex shape. You could spend your lifetime studying that shape, and you would never more than scratch the surface. Because there's an infinite amount of it that you haven't explored. So that's something to think about. Maybe a little glimpse of how heaven will be. Well, it made me think then, is there something special about that formula? I mean, maybe we just got lucky. Z squared plus c is maybe the only one that has that complex shape, that beautiful shape. What happens if I change the formula? Now, I found if you change c, multiplied by something, divided, added, whatever, it doesn't really affect the shape too much. It just rotates it or moves it or whatever. But if you change z, what happens? Well, we tried z squared. What happens if we try z cubed? Will we get an interesting shape? And the answer is yes, we will. This is the shape that you get if you try z cubed plus c. It's a different shape, a new one. There you go. This one's called a multibrot, because the Mandelbrot, this is a multiple of the Mandelbrot. And the main shape that you see now, you notice everything has gone up by 1. Remember, the Mandelbrot had a cardioid, which has 1 valley in it, and it has circles growing off. Circles have no valleys in them. This it has a shape called a nephroid, which has 2 valleys, one there and one there. And instead of circles growing off of it, cardioids grow off of it, which have 1 valley. So everything's gone up by 1, which kind of makes sense. We increased z squared to z cubed. That main shape, the nephroid, is what you get when you take a circle half the size of another and roll it around the original. See? That's a nephroid. Why does it make that shape? I have no idea. That's wonderful. What happens if we zoom in on this? Or frankly, one of the things that we can do too is what happens if we make z in between 2 and 3? What if you gradually change it? You make z to the 2.1, 2.2, 2.3, 2.4, 2.5, and so on. Then you could gradually see how one shape sort of morphs into the other. This is what it looks like when you do that. I thought that was kind of interesting. So you can see how the Mandelbrot set sort of becomes the multibrot set as you increase z. And you can see things are getting doubled. And some things get quadrupled. Like the baby version down here. Watch what happens. It splits into 2, and then another one joins it. So it splits into 4. You have 1, 2, 3, 4 baby versions. So some things get quadrupled. Most things get doubled. The one thing that seems pretty unchanged is the Valley of the Elephants. You notice that's the least changed, right? Everything else kind of is morphing and changing. That stays pretty much the same. So what happens if we zoom in on the Valley of Elephants? Do you think we'll still have elephants? Let's find out. There'd be elephants. How about that? Now, what's interesting here is the circles have become cardioids. And remember, we had 1 elephant on each circle? Infinite number of circles and infinite number of elephants. Now they've doubled. So instead of having 1 elephant on a circle, we now have 2 elephants on each cardioid. The circles have become cardioids. Now think about that. We had an infinite number of elephants, and now we have twice that many. Yeah. That blows my mind. I hope it blows your mind. It just gives you a little glimpse into what it's like to think infinitely. Some of these things that we think, how can God do that? Well, you know, He's infinite. And infinite doesn't always obey our expectations. If we zoom in on the elephants, what do we get? Again, you get that spiral trunk. If we zoom in on a section of that spiral trunk. PowerPoint just doesn't like me. There we go. There's the strands that you see. Now the interesting thing, instead of having bow ties like we had before, where you had those 2 spirals, this time they multiply. Now we have 3. 1, 2, 3. And they go from 3 to 9 to 27 and so on. It's all the powers of 3 this time, which makes sense. We're using z to the 3rd power. And again, if you zoom in on the center of that, you get not a baby Mandelbrot, but a baby multibrot. You get a small version of the original. There it is. See how similar it is? There's the original, there's the baby version. Remarkable. So it's fractal as well. It has smaller versions built into itself. It is fractal. And just to give you an overview, what happens if we do z to the 4th? Well, there's what you get. Now, at this point, I'm looking for patterns, right? Because z cubed gives me sort of a twofold shape. It's as if there's a mirror right here. This top part is a reflection of the bottom part. So it's got sort of a twofold structure. And the power was 3. When the power is 4, you get a threefold structure. 1, 2, 3. When you have 5, you have a fourfold structure. When you have 6, you have a fivefold structure. And so on. Apparently, the number of lobes you get down here is 1 less than the power of z. Which means if we go z to the 7th, we can get snowflakes. And if we zoom in on this, do we have baby snowflakes? We sure do. You can zoom in on various sections of it, and it's quite beautiful. And you get little baby snowflakes in there as well. Amazing. I tried negative powers of z. I'm just curious to see what happens. This is what happens when you have z to the negative 2. The negative power is the reciprocal of the power, so this is 1 over z squared. Interesting. Now, remember, black means it does belong to the set. Color means it does not. And you'll notice the exterior is now black. All these points belong. This little section here is the only section that doesn't. The rest of the universe belongs. Okay? So it's inside out. The Mandelbrot, most of the universe was empty except for the Mandelbrot. The universe is filled. Most of the universe does fit into that formula except for this little section in the middle. Little cookie cutter cut out there. And apparently, and this belongs to the middle. Now, if we zoom in on this as a fractal, I will say that this overall shape does not repeat anywhere, that I've been able to find anywhere. But, as you zoom in, you'll find these sort of pebbled structures, which I find to be quite beautiful. And if we zoom in on that, is it fractal? Does the same kind of shape repeat infinitely on smaller scales? What do you think? Yep, it does. You can zoom in on that forever, and it'll just continue to be beautiful. You have petals upon petals. Look at the structure and the beauty that the Lord has built into the abstract world of mathematics. Quite amazing. So there's z to the negative 2. It gives you a threefold structure. Z to the negative 3 gives you a fourfold structure. Z to the negative 4. Z to the negative 5, another way to make snowflakes. This time, inside-out snowflakes. So it's really remarkable. Okay, so what does all this mean? We just looked at pretty pictures of one. What causes the beauty in fractals is what I want to know. What causes the complexity in fractals? The fact that they are able to add and multiply, and they have these intricate shapes that the more you zoom in on them, the more complex they seem to get. How can we make sense of what we're seeing here? Let's start with the beauty in fractals. What causes that? What are some possibilities? Well, is it the man-made color scheme? I chose the colors for these, and you can choose any color you want. By convention, black always points on the set, but it's anyone's pleasure as to what the color should be on the exterior. Is that what makes them beautiful? I would say no, because even if this is very pretty, but if you subtract the color, make it gray, it's still beautiful. There's something about the shape that is very attractive to the eye. It's beautiful. Now, I do think the color enhances the beauty. It's a little bit like the way salt brings out the flavor of your food, but it doesn't create that flavor, right? And so it's the same. I think adding color to that to shading, it really helps you to see the shape a little better. It makes it a little prettier. But that's not what creates the beauty in there. The beauty's already there. Did the computer create the beauty? No, because remember the first 2 points we checked manually. Remember we checked to see if -1 was part of the Mandelbrot set. We checked to see if 1 was part of the Mandelbrot set. You could do this all by hand. It would take you forever, but you could do it. You don't actually need a computer. The computer just does it fast. And that's why these weren't discovered really until the 80s, when computers became fast enough to check all those points very, very quickly and fill your screen. So the computer did not create the beauty, because all it's doing is following the laws of mathematics and seeing if z gets big or if z stays small. That's all it's doing. The computer doesn't create the beauty, it just reveals it. It allows us to graph these plots quickly. And so it's kind of like, microscopes don't create bacteria. They just allow you to see them very closely. And so the computer allows us to see these shapes that already exist in the abstract world of mathematics. Did people make this? Did people make the Mandelbrot set? It's named after Benoit Mandelbrot. Its discoverer, but he didn't create it, right? He was surprised. Human beings were surprised when they plotted this and they saw this weird shape and then they zoomed in and saw this incredible beauty. You wouldn't be surprised by something you yourself made, right? You wouldn't create something and say, well, how about that? I had no idea it was going to look like that. That wouldn't make any sense. People did not make this. People were surprised by this. And by the way, people can't make something that's infinite anyway, right? We don't have the time. And the Mandelbrot set is infinite. Apparently, the beauty is somehow built into math. That's the only explanation. I'll grant that people did select the formula z squared plus c, but what we found is when you change the formula, you still get beauty. So it doesn't really matter too much what formula you pick. What causes the complexity in fractals? The fact that they obey laws of math, and when you zoom in, they get more and more complicated, and they have baby versions of themselves. Again, did the computer create it? No, because the computer simply revealed what was there. When these shapes were first discovered, some people speculated that maybe it was a mistake, an artifact of the computer, that maybe the map of the Mandelbrot set doesn't really have baby versions built into it. That's since been disproved. Mathematicians have established that indeed those baby Mandelbrots are real. They do exist. They're part of the plot. It's not an artifact or a mistake in the computer code. You can write different codes and you get the same answer. Did human beings create it? We can't create something that's infinitely complex. No human being sat down and said, well, I think I want to draw a cardioid and then attach an infinite number of circles to it. You can't do that. We don't have time to do something that's infinite. And by the way, the Mandelbrot set is not just infinite, it's infinitely infinite. Because each baby, all those little baby versions, all of them had a tail, and they have a baby on the tail, and so on and so forth. Each baby has an infinite number of babies, so it's an infinity of infinities. As mind-blowing as that is. Not a problem for God. Did the formula create it? No, the formula revealed it. We had to put numbers through that formula to get the shape, and we found if we changed the formula, you still get beautiful shapes, you still get complex shapes. The complexity is somehow built into math. Built into numbers. What is math? Mathematics is the study of the relationship between numbers. That's how it's defined. And I'm going to ask, what are numbers? And the reason I do that is because some of these things that we take for granted, that we use every day, they're kind of hard to define. How do you define a number? You ever thought about that? I consulted a number of dictionaries before I got anything that was even remotely reasonable, but the best I could come up with, this is in the dictionary, is that numbers are a concept of quantity. That's pretty good. That's a good definition of a number, a concept of quantity. And so if you have 3 apples, apples are physical, threeness is not. Threeness is a concept of the number of apples that I have. I can remove the apples and still have the conception of threeness. What do 3 apples and 3 dogs have in common? Threeness. Okay. That's something you can abstract away. The number is something you can abstract away from the instances. So if numbers are concepts, well, then they're abstract in nature, right? They're not physical, they exist in the mind. The concept is something that exists in your mind. Okay, this is important. Because you can write down a number like 3. Is that the number 3? That is a representation of the number 3. Because if that's the number 3, and I destroy that, then I've destroyed the number 3. And students will have to count 1, 2, 4, and so on. Well, that would be ridiculous. That was simply a representation of the number 3. And destroying it does not destroy threeness any more than destroying a picture of a horse destroys the horse. Okay, it's just a way of representing threeness. You understand that? It's a numeral. Numerals are not numbers. Numerals are representations of numbers. Okay? Laws of math are conceptual. Where do laws of math come from? Well, in the biological world, when we have things like dogs and pigeons and horses and so on, how do evolutionists explain that? Evolution. They would say that these complex critters started out as something very simple, and then they got more and more complex as more information is added to the DNA, which we never observe, but nonetheless. Can that apply to numbers? Can it apply to laws of math? No, because they don't change. It's not like 7 evolved from 3. Right? 7's always been 7, 3's always been 3. Numbers don't evolve, right? They can't evolve, so that doesn't make any sense. That's not an explanation of where laws of math come from. Were laws of math created by people? Some people think that. They think, yeah, human beings created math. No, we discovered math. We didn't create it. If we created it, we could have created it differently. Somebody could have sat down and said, you know what, I'd like 2 + 2 to equal 5. Now, you can try that, but it's not going to work. Because you don't make laws of math. We discover them. We discover that when you take 2 things and replace them with 2 more things and you count the total, it's always 4. That's a discovery, not something that we invented. People didn't create laws of math. Did they come from the universe? Some people think that, but math goes beyond the universe. It is true that the universe obeys math, and that's something I'm going to come back to a little bit later. But math can go beyond the universe. For example, in calculus, one of the things I found very interesting in calculus was when you can calculate things like the volume of a sphere. Now maybe you know the formula. You know, it's 4/3 pi r cubed. Okay, but how do you know that? In calculus, you can prove it. You can prove that indeed the volume of a sphere is 4/3 pi r cubed. But the cool thing is you can also step it up and say, what if the universe were 4-dimensional? What would the 4-dimensional equivalent of volume be for the 4-dimensional equivalent of a sphere? And you can calculate that, and you get an answer. And I forget what it is. Something pi squared r to the 4th. I forget what the coefficient is. But you can prove that. And you can step it up any number of dimensions you want to, and you have an answer that's meaningful and reasonable. So math goes beyond the physical universe, because the physical universe only has 3 spatial dimensions as far as we know. Whereas in math, you can have an infinite number of dimensions. There's a branch of mathematics called Hilbert space, where you have an infinite number of dimensions, and it's sensible. So laws of math don't come from the universe. They go beyond the universe. You can do things in math that are infinite. In calculus, you can add an infinite number of things and get an answer. In the universe, we probably don't have an infinite number of things in the universe. But in any case, I would suggest that laws of math stem from the mind of God. Now that makes sense. And it makes sense of the properties of laws of math. Because God's infinite, and so his thinking is infinite. It explains why laws of math are conceptual, why they have the properties that they do. Laws of mathematics are conceptual. They exist in the mind, right? They're universal, meaning they apply everywhere, right? Laws of math work the same way in the Andromeda Galaxy or on the moon as they do on Earth. Just like laws of logic, the astronauts were not concerned that math would be different on the moon. They figured it worked the same way as it does on Earth. They're invariant, meaning they don't change with time. It's not like 2 + 2 = 4 on Thursdays, but not on Saturdays. That would be ridiculous. They're exceptionless. It's not like 2 + 2 = 4 most of the time, but every now and then it doesn't. Now, how do we explain the existence of laws of mathematics and the fact that they have these properties? Well, it's because they stem from the mind of God. God's thoughts are conceptual, so of course laws of mathematics, being a reflection of God's thinking, would be conceptual. God is omnipresent. He's everywhere. His power is immediately available everywhere in the universe. Therefore, laws of mathematics would be universal. God's mind upholds the entire universe, after all. They're invariant because God doesn't change. Therefore, his thinking doesn't change. God can step into time and do things, but he himself is beyond it. And so his fundamental reasoning about numbers does not change. And they're exceptionless because God is sovereign over all reality. All truth is in the mind of God. Therefore, there can't be any exceptions to mathematical truths, because God's mind is in control of everything. And this presents a huge dilemma for the naturalist, those who reject the Christian worldview and say, no, the universe is all that there is. Because you see, laws of mathematics are conceptual. They exist in the mind. But laws of mathematics also existed before people, right? Because think about Kepler's law, for example. Kepler's 3 laws of planetary motion. Kepler's 3rd law says p squared equals a cubed. The period of a planet in years squared is equal to its average distance from the sun in AUs cubed. Now, planets were orbiting perfectly fine before people, right? By a few days. In the secular view, by billions of years. So wait a minute, if mathematics is the product of a human mind, then how would the planets know how to orbit before human beings came around and told them how to do so? Right? You see, it doesn't work. On the one hand, we know mathematics, the laws of mathematics are conceptual because they deal with numbers. Numbers are conceptual, they exist in the mind. And yet, laws of mathematics existed before people, so they can't be in the human mind. Now see, in the Christian worldview, that's not a problem because we have a mind before human minds, the mind of God. We have a mind before the universe existed, the mind of God. Right? And so this makes sense in the Christian worldview, but it makes no sense in the naturalistic worldview. Right? Because the naturalist, he doesn't have a mind before human minds, and yet he believes that laws of mathematics somehow applied before human minds came around and invented them. It doesn't work. There are also what we might call physical fractals. The shapes we've looked at so far, the Mandelbrot set, that's a plot of a mathematical set. It doesn't exist physically. It does exist in the mind of God. And now in our minds, now that we've discovered it, at least a rudimentary map of it, you can't touch the Mandelbrot set or see it in a telescope or accidentally stub your toe in the Mandelbrot set because it's conceptual. It exists in the mind. But there are physical fractals that you can touch, that you can see in the physical universe. Now, I will point out that physical fractals are a little different from the Mandelbrot set, because the Mandelbrot set goes on forever. You can zoom in on it and get babies and babies and babies and so on, minis and minis. The physical world, eventually you get down to the level of atoms and then they're not fractal anymore. But nonetheless, there are some things in the physical world that approximate fractals. And one example would be snowflakes. Snowflakes have a fractal shape to them. Most of them are six-sided because of that has to do with the shape of the water molecule. But when you zoom in on a snowflake, it kind of looks like the overall structure. Maybe it doesn't repeat exactly, but the smaller structures within it resemble the overall structure. And so these little gems from heaven that the Lord sends us every year, and we scrape them off our car, but they're actually quite beautiful when you zoom in on them. They're a fractal in nature. The stuff that grows on your windows under the right conditions. And when you have sufficient humidity within your house and it's cold enough outside the house and that stuff grows on the window, it tends to form fractal shapes. And some of them can be quite beautiful. And so you can see how the individual structures look like smaller versions of the entire structure. Ferns, the way ferns branch is fractal, because a fern has a main stem, and off to the side are leaflets. But each leaflet has a main stem, and off to its side are leaflets. And on each one of those is a stem, and off to the other side are leaflets, and so on. It does stop at some point with physical fractals, but you can see it branches and branches and branches. I even found fractal broccoli. How about that? So I guess broccoli is good for something after all. There you go. So this is called Romanesco broccoli. And it's you can see that it's kind of a cone shape, but it's made up of smaller cones. And we zoom in on those smaller cones, we find the smaller cones are made up of smaller cones, which are made up of smaller cones. Very interesting. The way coastlines fragment is fractal, in terms of the way they branch and they branch into branches and branches and so on. Mountaintops, when you look at mountaintops from above, they're fractal in nature in terms of the way that you see how the branching pattern there, how it branches and then the branches branch into smaller branches and so on. Clouds are often fractal. Am I looking at a huge section of the sky right here? Or am I zoomed in on a very small section of cloud? You don't know, because clouds have the same kind of structure on the large scale as they do on the small scale. That's fractal. The way lightning branches is fractal. Because you have a main bolt and it branches into smaller bolts and they branch into smaller ones and so on and so forth. It's quite beautiful, actually. And you can actually watch that branching in real time. If you have, with high-speed photography, you can see how the lightning branches until the leader connects, and then most of the current goes down the leader then. But it's really quite beautiful, and it is fractal in nature. So why do fractals occur both in math and the physical world? That's what I want to know. Because you have this shape right here, that's a multibrot. That only exists in the conceptual world of mathematics. That's something that, in order to see that, you have to plot it on the computer screen. Because it's a shape, it's the shape of a mathematical set that's plotted in the Argand plane, where you have the real number on the x-axis, the imaginary number on the y-axis. On the other hand, that you can see every winter. But they're similar. They're very similar. This right here is part of the Mandelbrot set, the way it branches and branches and branches. That's non-physical. On the other hand, lightning bolts are physical. They're made of electrons, flowing electrons. which are physical particles. That particular shape, that may look like a plant, it's not. That's a mathematical graph. It's called a Barnsley Fern. And it's fractal because each leaflet of this Barnsley Fern is the entire fern. Let me show you. Take the entire fern and it becomes a leaflet of itself. See that? You do that forever. Each leaflet is the entire fern. So that doesn't exist anywhere in the physical world, but these do. Interesting. That shape right there, mathematical graph, does not exist in the physical world. That stuff grows on your windows. It does exist in the physical world. This is a mathematical graph of cones upon cones upon cones. It does not exist in the physical world. This, unfortunately, does. This shape right here, part of the Mandelbrot set, Valley of the Double Spirals, that double spiral structure that you see there, you can't see that in a telescope because it exists in the abstract world of mathematics. But that you can see in a telescope. I've seen it. Local galaxy. Similar. Why is it that fractals occur in math, which you can't touch, and in the physical world, which you can? Why is that? Now, one answer might be, well, the physical universe obeys mathematical laws. And that's not a bad answer as far as it goes. I mean, the universe does obey math. It obeys equations like E equals mc squared and F equals ma, right? And so if fractals can occur in math, and the physical universe obeys math, it stands to reason that the physical universe can have fractals in it, right? That makes sense. But then I'm going to ask the question, why? Why does the physical universe obey mathematical laws? That's what I'd like to know. Because mathematical laws are conceptual, they exist in the mind. The physical universe does not exist in our mind. How is it that the physical universe obeys mathematical laws? That's a puzzle. Well, not in the Christian worldview, because in the Christian worldview, mathematics is a reflection of the way God thinks about numbers. And the universe is upheld by the mind of God. Therefore, the universe will obey mathematical laws. The same mind that is responsible for laws of mathematics is also responsible for upholding the universe. That's why the universe has to obey math, because it's under God's control. Makes sense in the Christian worldview. But the secular worldview cannot cogently answer that question. They've tried. They've failed. They can't answer it. They can't explain why we have laws of mathematics, why they have the properties that they do in terms of, we talk about laws of mathematics are the same everywhere, and they don't change with time, and they're abstract, and they're exceptionless. And they cannot explain why the universe is compelled to obey mathematical laws. The secularists cannot explain that. They have tried. There was a physicist, Eugene Wigner, brilliant guy, apparently not a Christian. He was a Nobel Prize winner. This is no slouch. This is a PhD physicist who won a Nobel Prize. And he wrote an article decades ago called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, where he attempts to tackle this question: why is it that the physical universe obeys mathematical laws from a secular perspective? What is his conclusion? He's puzzled by it. He says, it's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to divine them. He says it's remarkable enough, it's amazing enough the universe obeys laws. That's amazing. What's even more remarkable is that we can discover some of them. And it's funny too, because he goes on and says, this is not something you would expect given Darwinian natural selection, that we would somehow be able to do that. Very interesting. It's an interesting article. I highly recommend it. Again, he's not a Christian as far as I know. He's just honest. What does this brilliant physicist conclude? And he is brilliant. I'm not putting him down. He's smart. God hasn't opened his eyes, you see. What is his conclusion then? Here it is. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. Isn't that interesting? He has no answer. From his perspective, it's just, that's interesting. What an amazing thing that the universe happens to obey math. He cannot explain it. Christian can. Christian says, hey, mind of God's responsible for math. Mind of God holds the universe. Of course the universe will obey math. It has to. But you can't answer that from a secular perspective, which means secularists cannot explain fractals. They can't explain why we find such beauty built into numbers. And it is beautiful. You've seen the shapes. It's incredible. That makes sense given the God of the Bible, who has a sense of beauty. And the way he thinks about numbers is obviously beautiful. We've seen it now. It is beautiful. Secularists can't explain that. Our worldview, we can explain why we find physical fractals in the universe. Because God's mind, the same mind that has these fractals in the abstract world of mathematics, upholds the universe. So of course you're going to find fractals there as well. Makes sense in the Christian worldview. So we've seen that there's beauty of infinite complexity built into numbers. Pretty amazing. And it is infinite. You can zoom in on the number set forever. It'll just get prettier and prettier the more you zoom in, and more complex. It's beautiful. Numbers are abstract conceptions of quantity. They exist in the mind. Concepts require a mind by definition. And yet, it can't be the human mind because numbers existed before people did. Now, humans developed numerals the way we choose to write numbers, and you can't do that differently. You can have Roman numerals or Arabic numerals, right? But it represents the same concept. The concept we didn't come up with. God did. Numbers are a reflection of the way God thinks. The secular worldview cannot account for the existence and properties of numbers or any mathematical truths, because they don't have a mind before human minds, let alone a mind that can control nature. Numbers existed before people, yet they are conceptions, meaning they require a mind. That's a problem for the secular worldview, because they don't have minds before people. In the Christian worldview, we do. Laws of mathematics are universal, invariant, abstract entities, because God is omnipresent, himself invariant, unchanging in time, and his thoughts are abstract, as all thoughts are. The physical world does contain fractals. It does. And that makes sense in the Christian worldview, but the secular worldview cannot account for why the physical universe obeys mathematics. It's a miracle. To quote the Eugene Wigner, the universe is controlled by the mind of God. So in the Christian worldview, I can make sense of why we have fractals. I submit to you, there is no secular explanation for anything we've covered today. You just can't make sense of it. It really reveals the mind of God.